Okay, this is our 5th video by my count, and this is on the subject of total correlation spectroscopy, as it's called, or TOCSY. This evolved from COSY, I suppose, is the way to say it. Here we have the COSY spectrum of this compound isoleucine that the structure is drawn out for you. So remember, in COSY you have symmetrical halves. Let's just walk our way through this really briefly. Starting from this d-shielded end, the signal for the methyl protons at 0.93 is here. It's a triplet, as you would expect, by the way. It correlates in COSY to the 1.25 and the 1.46, both of which are at the adjacent position. So that makes sense. Notice it does not correlate to the 1.97, which is the next one down the line. There's nothing there. And as you continue here, so the 1.25 and the 1.46 here and here on the diagonal correlate to each other. So there's geminal coupling. They correlate to the 1.97, which is one marching over to the right, one position. They both correlate to that, right? And they do not correlate to the and they also do correlate, I'm sorry, to the 0.93, both of them. And then this one's just a symmetric correlation, so we won't go, we shouldn't do that probably. Okay, so as we continue down, the 1.97 occurring here on the diagonal correlates to the 1.46 and the 1.25 that are just to its left as we look at it. It correlates to the 1.00 here, as I'm circling it, which is over here, and that makes sense because it's on an adjacent carbon. So far we're seeing all of these COSY correlations, these COSY correlations, and these COSY correlations. Finally, we have the 3.66 way down here on the diagonal, correlating only to, as you would expect, the 1.97. So we see that correlation. And notice the methyl at 1.0 is too far for a COSY. So this seems like it's, and it is, providing a lot of additional information. And it enables us to walk our way through the molecule to some extent. But let's say, hypothetically, now, I'm going to use a different color, that we had a molecule, and I'm just going to scroll down below, a hypothetical peptide here that has not just one, but two isoleucines. Now, they're going to be very likely in different enough chemical environments that some of the signals will be more or less de-shielded. But basically, and this is a peptide, this is drawn in a little bit different way, but basically what we've been looking at, if all of these essentially aliphatic protons, and going back up, this is this whole, they're this in this whole region. So imagine if we had another isoleucine 2 down here, that had another whole set of those. Odds are what we're going to see is a bunch more signals in this region. Everything's sort of, and a lot of overlap. So you get kind of quite a mess like that. Now, what we're betting on often is that the alpha proton, as it's called, here and here, that these are going to be different enough in chemical environment to offset. And if we go back up to the spectrum, let's say we would have another signal here, for example, of some multiplicity, and some cross peaks there, for example. that are offset enough. And so if we can distinguish all of the blues from the oranges, then we could use this information here on the more deshielded end to establish two sets of peaks. So that's kind of one of the main advantages of TOCSY, which reveals all of the correlations within a spin system. So isoleucine is all one spin system. And so what we're going to see in the TOCSY, by comparison, is, here's the full TOCSY spectrum here. You're going to see all correlations within the molecule. So I'm going to draw this out again real quick. Isoleucine. And notice we're not seeing any of the signals for the exchangeables. And this was at 1.00 if I recall. And 1.97, 3.66, 1.25, 1.46, and delta 0.93. So in TOCSY, what we expect to see is not just the correlations between, say, 0.93 and 1.25 and 1.46, but now you should see a correlation from 0.93 to 1.97. So do we? Here's the 0.93 on the diagonal, excuse me. And yes, we do see a correlation from it to 1.97. Now I'm going to talk about these signals a little bit more. I have some expansions, but the 0.93, if you go down the other way, it's a little bit better. And actually, that's the point of this expansion on the right, to be honest. So it's just showing you that the correlations are better revealed in that diagonal, strangely, to some extent. So 0.93 does very clearly see 1.97. So notice they're not adjacent. That would be a long-range coupling, but in TOCSY you see all the correlations. So we should see a correlation between 0.93 and 1.0. And in fact, yes, we do see that. They're very close to each other. We should see a correlation between 0.93 and 3.66, and this is getting more to the point of the discussion. One of the key points, 0.93 to 3.66, there it is, coming all the way down in this direction to 3.66 on the diagonal. Remember, we were hoping that if there was a second isoleucine, say here, that we would see another set of signals for it. And so what we're doing here is that if we had the TOCSY spectrum of that hypothetical complicated peptide, we would have a set of purple signals and a set of green signals, where the purple signals in all likelihood are going to overlap in this region here with the greens, but here they're distinctly separated. So you end up being able to fish out the two separate spin systems, starting with this information, or really, when you think about it, any information from any of the signals that are well resolved. So there's a good chance there'll be some other signals that are well resolved, but really in this region, especially for peptides, it's going to be a really crowded mess. So But the ones that are distinct will allow you to fish out some, or if not all, of the ones that are overlapped in the other parts that are overlapping. The expansions, so the expansion above simply shows you this upper part of the TOCSY spectrum focusing on the 1.0 ppm broad region. It's kind of showing you that there is the information that we saw looking down in the other direction. It's just harder to see. So in the future, or with a higher resolution instrument, most likely all of these cross peaks, as they're called, would be finer resolved. Something like that. I didn't mean to make that look like a cross peak, but they would be more resolved like that. And so you wouldn't have these issues. Higher resolution at higher field strength solves a lot of problems. But even then, you're going to run across a molecule where you need techniques like this to resolve overlapping signals. So perhaps the take-home message for now is that most of our 2D NMR techniques were done to sort out complex overlapping signals. TOCSY is a particular case of that. Amino acids form peptide chains. That's one of the main applications. Another easy one to think of is carbohydrates, so a chain of repeating sugars. All right, we're going to move on to the next techniques that really are more important. COSY, and from then on, it's on to HSQC and HMBC. So tomorrow in our Zoom session, we'll probably talk about COSY, TOCSY, NOSY a little bit, and then next week we'll start into this really great stuff that is extremely useful. All right.